So one of our last lectures, we were talking about errors. We talked about absolute error. What's an absolute error?
Absolute error is the actual value minus measured value.
Yeah, it doesn't really matter what order you put in, actual minus measured or measured minus actual. It's just that's what those little lines around the outside mean. Is it doesn't matter which one's bigger. It's just the difference between them, no matter which one's bigger. So if an object is actually 14 1/8 inches, and we measure it at 14 1/4 inches, the absolute error, the difference between them is 1/8 of an inch. If the actual is 2 7/8 inches and we measure it at 2 3/4, this time the measured value is smaller, but the difference is still just 1/8 of an inch. So both of those have an 1/8 inch absolute error. Yes. Relative error is the absolute error divided by the actual. So like for this first one, it's 1/8 over 14 1/8. .0088. For this other one here, it's 1/8 divided by 2 7/8. .0435. Now, along with that, there's something called a percent error. Some textbooks treat it separate from relative error. Some textbooks treat it the same. They're really measuring the same thing. It's just a different way of expressing it. So like the percent error here, just remove the decimal point 2 spots. That's 0.88%. Here you move the decimal 2 spots. That's 4.35%. This is a great example, by the way, of how a 1/8 inch absolute error. How do you know the absolute error really isn't enough to evaluate an error? Is it okay to be off by 1/8 of an inch? Well, if we have 14 1/8 inches, being off by 1/8 inch is less than 1%. That might be okay. It's kind of on the edge. A lot of times it's like a 1/4% is what most of them, what our allowances are. But if it was only 2 7/8 inches, like this one here, being off by 1/8 of an inch is over 4%. That's definitely not acceptable. So the allowable absolute error depends on how big the original piece is. The bigger the original piece is, the further it can be off and still be acceptable. The smaller it is, the more precise you have to be. And we've talked about that degrees of precision and all, possible error in measurement and stuff before. This is talking about what's actually happening. Now, if you have a piece on a schematic or whatever that is labeled like this, what's that mean? Okay. 3/1000 tolerance. And actually, this is actually what's called an allowance. A lot of people use the term tolerance there. That's not quite the correct spot to use tolerance. It's a 3/1000 allowance, which means you can be 3/1000 smaller. So from the 450 thousandths, I can subtract 3/1000. So 447, right? Or, yes, I can go bigger. From the 450 thousandths, I could add 3/1000. 3.453 inches. So it gives me a range possible values. That 6 thousandths, that is the tolerance. It's double the allowance is your tolerance?
No,
with a range? Okay. This, what is set up here, this is called an absolute allowance. Or absolute tolerance, depending on whether you're using the terminology correctly or not. Because an absolute is plus or minus 3 thousandths, period. But you might have parts where you're running several of a part, and they might be different sizes, but the same part, same type of function. It is possible to have a piece labeled like this.
What would you say would be a good definition for absolute allowance? Sorry.
The plus or minus is a measurement. It's a number of inches or millimeters or whatever. This here is what is called a relative allowance. Again, depending on how technical you're being with the term, sometimes called a relative tolerance, where the allowance is a percent. So the first thing you got to do here is find the percent. 0.4% is 0.4 out of 100. How much is that out of 0.650? So you'll cross multiply and divide. 0.650 times 0.4 divided by 100 is 0.0026. So what this really is 0.625 inches plus or minus 0.0026 inches. Make sense? Actually, 2 thousandths, 26 ten thousandths.
Relative allowance?
Yes. That's the percent is the relative allowance. We converted it. This here is an absolute allowance. The purple is, because we converted it from a relative back to an absolute. Sure. That's a percent, yeah. Okay, so now the textbook, this textbook often does use the term tolerance instead of allowance. So they're talking about the plus or minus instead of the whole range, which they said is a little bit sloppy, but they're taking a little bit of liberties with the terminology, which we'll live with. Let's say you have a given length of 1.200 inches and an allowance of plus or minus 0.012 inches. Upper limit is just going to be that plus that, right? So it's going to be 1.212 inches. Make sense? Lower limit is going to be this minus that. Yeah, 1.188 inches. That's your upper and lower limit, your range. This book, by the way, uses the term tolerance interval or tolerance range for what's really a tolerance. So if you see tolerance range and actually subtract those, it would be 0.024. What if I give you that the allowance is plus or minus 0.008 inches. And the upper limit is 0.923 inches. Find lower limit given length. Well, how do I get from upper limit to given length? So I got to subtract it back out. 0.915 maybe. Yep. And now from there, now I can find the lower limit. I subtract the 0.008 again to get 0.907, right? One of the most common applications in automotive electronics is resistor color code. Yep. You guys talk about these at all? The little color bands on the resistors?
Oh, yeah.
Remember the sequence of colors?
We really only see those resistors, the color bands on circuitry. We don't do a lot of circuitry.
Not anymore. No. Pull the whole board and replace it.
But it's still something we need to know for electrical, in case we do run into it. We have to answer your question.
No, it's kind of politically incorrect, but the way I remember this, bad beer rots our young guts, but vodka goes well. Get some now. Yeah, I know.
Are you sure?
So each of these has a value. For example, black is 0, brown is 1, red is 2, 3, 4, green is 5. Well, you'll see the connection here. Gold, silver, and none do not have any tolerances attached to them. Or any, well, I gotta be careful. I'll show you that in just a minute, how that works. Those are the actual values. Then there's tolerance here. If there's a tolerance band as a location, gold is plus or minus 5%, silver is plus or minus 10%, and none is plus or minus 20%. None, or sometimes brown. Is it brown or black? No, it's black. Is used for the plus or minus 20%. I'm going to take a peek just to make sure I don't use the black. Sure. To get the colors in?
Yeah.
Yep, gold, silver, none. None. And then, yeah, none, like I said, sometimes none is black is used instead of none for the plus or minus 20%. I've always used none for everything I've worked with. Though these are typical, there is, however, some brown that's plus or minus 1% and red that's plus or minus 2%. Those are your military tolerances. You know, military resistors and stuff require much tighter tolerances. Well, do you know those get produced, right? a little bit of a, yeah, black is the 20%. It's funny because there isn't a special process. They don't change the process for producing resistors that have a 1 or a 2% error. They just produce a large batch of resistors and they test them. And the ones that happen to come within 1 or 2% of what their marked value is, they get thrown in the bin to get marked with a brown or red tolerance band, and those get sold to the military. A lot of people don't realize that companies that do military contracts, almost all of them lose money on the military contract. So you hear all the complaints about companies getting rich off military contracts. It's really kind of misplaced anger. Like, let's say the military contracts me to produce 1,000 resistors that have that plus or minus 1% or 2% or whatever, the military grade. I might have to produce 20,000 resistors to get 1,000 of them that meet that specification. Well, the military is going to pay for all 20,000. They're not paying just for the 1,000 they get. In fact, they're not going to pay me for all 20,000. I'm going to lose money on that 1,000 resistors I give to the sell to the military. Where I make my money is I got that other 19,000 that wasn't good enough for the military. They're good enough for some other stuff. So there's a secondary market, and that's where most of the military contractors make their money, is selling off the rejected parts on the secondary market, because they're still very high quality parts, just not quite. Like for a nut and a bolt, you put a nut on a bolt, you can finger tighten it because there's a lot of slop between the threads of the nut and the bolt. Well, that's also why when they're on something that vibrates, they come loose. Well, in the military, you cannot have a nut come loose on a bolt. So theirs are very, very tight. There is no slack. Those threads in the bolt are almost exactly match the threads on the nut, to where even the smallest little burr, they're not going to turn. You cannot hand tighten a military nut onto a bolt. You can barely get it started, then you have to take a wrench because they're so tight tolerances. There is no room to vibrate.
So how do you know if it's cross-threaded or not?
Yeah, that's tough to know. Very tough to know. Well, there's breakdown, but it's not because bolts are vibrating loose. Well, they might still vibrate loose, but the chances of them vibrating loose are much lower because they don't have any room to vibrate. So very high tolerances. Black, because sometimes they use black. Then of course there's a times band or a multiplier band where gold is times 0.1 and silver is times 0.01, which we'll look at in a little bit. So on a resistor, there are 4 bands. The first 2 bands are the 2 digits. So let's say this first one is blue and green. Blue, of course, is 6 and green is 5. So that's 6, 5 is what those stand for. The third band is a multiplier band. Let's say that one on this resistor is red. Red is what number? 2. So that means times 10 to the 2.
Where's that 65?
6, 5. Blue is 6, green is 5. Blue 6, green 5. Nope. Those first 2 are digits. They're not added.
So that's the amount of resistance it has.
Well, 65, the second one tells you what does that 65 really mean. So the red is a 2, right? So that's times 10 to the second. So that's 6,5 with 2 zeros after it. So that's 6,500 ohms is what that means. And then let's say that the last band, the tolerance band, is silver. So that means that this is plus or minus 10%. Plus or minus.
Where did silver
Tolerance band. Right here. Settings plus or minus 10%.
Is it the tolerance or is it
That's tolerance.
allowance?
Well, it's technically an allowance, but they call it the tolerance band.
Alright. And it's only the first two digits that.
Yep. So like here, this is what this one, and there's usually going to be a little bit of an extra big space between the third and the fourth bands. The first band, red, is what number? 2, and green is 5. So this is 25 something. The third band is that multiplier. Orange is what number? 3. So that's 10 to the third. So that means it's 25 with 3 zeros after it, is what that means. Does that make sense? So it's 25,000 ohms. Gold means plus or minus 5%. Make any sense? Sure? Something like Tony the Tiger. It's sure great. Just saying. Let's say you've got yellow, blue, yellow. Oops. Oh, let's do this. Let's see. Gold, silver. So yellow is 4. Blue is 6. So those first two digits, 4 and 6, times 10 to the gold is what? 0.01, or 0.1, sorry. So instead of times 10 to the power, it's times 0.1. So that really means this is 4.6 ohms. And then silver is plus or minus 10%. So gold and silver can occur in that third band as a multiplier for really, really tiny resistances. In your book, page 198, exercise 4.7, 1 through 41, the odds. And on page 203, exercise 4.8, 1 through 29, the odds. That second page is the resistor color codes. I will tell you, resistor color codes, if it appears on a test, it would be an extra credit question. Because it's not necessarily, it's something that you saw in your other classes. They'll test you in automotive if you need to know it. I'm showing it to you as an application of it. But for you guys in automotive, it is something that's definitely worth your time to get good at.